So today I have a substitute, sorry, sixth period, and what I thought I would do is do a PowerPoint that includes sample problems on worksheets to teach you how to count protons, neutrons, electrons, and how simple it is to do a weighted average for a isotope of an element. So what I need you to do is recognize we're going to stop this guy midway, and the paperwork that you're going to need will be your 3 worksheets that you have on counting protons, neutrons, and electrons. The back side of that is more of the same. And the third worksheet that you'll need is one that says calculating the average isotopic mass. Now don't worry if you can't find them right now. As I'll show you in a moment, we'll have a screenshot come up for you to locate those. But a calculator will be good for the third worksheet. So as you know, or as you will know, when you view the vodcasts about the history of the development of the atomic model, researchers found out that indeed the atom was dividable and actually contains a central nucleus that has 2 particles inside of it. Those are the positive protons and the neutral neutrons. It's very dense. If you were to weigh, if you made the nucleus as big as that tiny little dot there on the exclamation point, if you would make that nucleus as big as that dot, you would find it would weigh as much as 70 cars. So it's heavy. Now inside it are positive protons. Easy to remember, both start with the letter P. Each proton has a charge of 1+, and that's exactly equal but opposite to the -1 charge that you would have on electrons, which are outside the nucleus. Now they don't weigh very much, as you can see, 2 approximately times 10 to the -24th grams, but they're almost 2,000 times bigger than an electron, so relatively speaking, they're a much larger particle. You find them in the nucleus, and this part is very important. The number of protons in the nucleus is called the atomic number, and it is a fingerprint that identifies an element. If you change the number of protons in the nucleus, you've changed the identity of the element. And we can only do that in nuclear reactions, unfortunately, not in chemical reactions. So that atomic number will always stand for the number of protons. The last statement, though, does it equal the number of electrons? Most of the time, but a lot of times atoms can gain or lose electrons. So in the upcoming worksheets, I'll give you examples of how to deal with when you have gained or lost some electrons. More on that later. So the neutrons that were discovered by Chadwick, and actually also by the Curie's daughter, Irene Joliot-Curie, she never gets any credit in the history books. They discovered the neutron. And if you have done your pre-lab worksheet problems, you probably figured out that it was hard to find the neutron because they're neutral. And if you're neutral, you're not attracted to a positive or attracted or repelled by a negative. It was kind of like hiding in plain sight. When they did locate and identify the neutron, they found that it weighed approximately the same as a proton. Now the number of neutrons is equal to the mass number minus the atomic number. Well, what's that mass number? If you add protons plus neutrons together, you get a mass number. If you subtract the atomic number, which is the number of protons, then you'll be able to find the number of neutrons. It's pretty simple math. And so what we're going to do is show you how to do that calculation in just a moment. The electrons live outside the nucleus. In fact, if you were to drop a dime in the center of our classroom floor, the nearest electrons would be found somewhere way out in the football field, relatively speaking. Electrons have a -1 charge. They're almost 2,000 times smaller than protons and neutrons. We're going to be spending an entire chapter on understanding where the electrons are because they contribute so much to understanding how chemical reactions take place. Now, if it's a neutral atom, the number of protons will equal the number of electrons. However, you can have not neutral atoms, and they're called ions. And the way that they got into an ion was they either gained or lost electrons. Now, this part is very important to pay attention to. If you think of an electron as a negative charge, if I lose electrons, I'm losing negativity, or another way to say that is, I'm becoming more positive. Somehow you have to train your brain to understand that when electrons go away, you're going to see a positive charge on the new ion that forms. Other atoms gain electrons. So if you're adding extra negativity to an atom, now you're going to change that into a negative ion, also called an anion. So let's look at an example of that. Sodium normally has 11 protons and 11 electrons. A positive 11 added to a negative 11, since each of them carries a +1 and -1 charge respectively, well, that should equal 0. But sodium often loses its outermost electron. And now, what if we had done that? What if we now have 10 negative electrons and 11 positive protons? We'll do a simple math problem. The positive 11 from the protons added to a negative 10 from the electrons shows overall that a sodium ion, which got formed by the loss of an electron, has a 1+ charge. Very important, losing electrons makes positive ions. Gaining electrons makes negative. And that's how we write it, and you don't even need to write the 1. If you have a 1 in chemistry, you can get lazy and just put the plus sign. Let's theorize. What if you had lost 2 electrons? That's right, the charge in the upper corner would say 2+, and so on. But sodium never does that, but again, more on that later. Now take a moment to shuffle through your notebook if you haven't already found it, and let's find this worksheet that I've taken a screenshot of. Notice at the top I've told you that the atomic number stands for the number of protons. The mass number equals protons plus neutrons added together. Now don't copy this information just yet. Watch the logic first. You will see brightly colored green keys that are underneath the movie screen. When you finish this side of the worksheet, you'll go up to the substitute, get a stamp, go over to the movie screen and correct and keep your own. So as I look at this problem, the first thing that you're going to do, and have a handy periodic table handy that's helpful as well, I'm going to put the symbol of the element in the first column. Easy, O is for oxygen. Now I'm giving you the atomic number, but you could have also found it on the periodic table. It's the number 8. And what that means is that it has 8 protons. So see how I've drawn a little line connecting those two columns? On this entire worksheet, the atomic number must equal the number of protons. Now the mass number stood for the protons added to the neutrons. In this case, the mass number equals 16. So if I know protons plus neutrons equals 16, if I subtract the number of protons, now I know that it also has 8 neutrons. So far so good. Unless we tell you otherwise, the number of electrons always equals the number of protons. So please make a note, if I give you the number of electrons, then we're going to be talking about an ion. If I don't give you the number of electrons, then we're talking about the same as the number of protons. Let's try another one. Lithium is symbolized with a big L, little I. Be very careful. First letter of the element symbol is a capital letter. The second one is a small letter. Its atomic number is 3. Well, that was given to me. This time I haven't given you the mass number, but I have told you the number of neutrons. So once again, atomic number is the same as the number of protons, so I quick plug in a little 3 there. If you want to, you can go right over there and put a 3 in the electron column, because in this one it's a neutral atom. Now go backwards, add neutrons plus protons to get the mass number. So far pretty simple, and pretty much the rest of the worksheet is like that, except let's take a look at calcium, and then I'm going to pause for a little bit and have you guys work on these worksheets. And I'll show you the back side of this thing as well. And after you've had a chance to correct it and stamp it and check it and get good at it, then we'll talk about the isotope worksheet. So now this time, how come Miss Doherty put a Ca with a 2+ charge here in the symbol column? Well, let's do the math. It's calcium, so off the periodic table, I've looked up or was given the fact that its atomic number is 20. Boom, I put a 20 right there. Hey, I got the mass number this time, 40. I subtract 20 from it. Now I've got the number of neutrons. But this time on the far right, I'm pointing out that it doesn't have 20 electrons. Calcium often can lose its outermost 2 electrons. So now I only have I've lost 2 electrons and I only have a total number of 18 electrons. What that means, if you lose 2 electrons, you're losing negativity, you're becoming more positive. How much more positive? A 2 plus positive charge ion must be written there. So that's the basics of this worksheet. I think there's one farther down where you might have to go get the mass number off the periodic table for the element, and it's okay to round off to the nearest whole number. But as you'll see in a moment, mass number is not the same as atomic mass. And let's take a look at the back side of the sheet. On the back side where it says ions and isotopes, exact same thing. The only thing that's different is get comfortable with this notation. This is called a nuclear symbol, and either they're both on the same side, or sometimes they put the numbers kitty-corner to each other, but it still means what we've learned all along. The number on top, the bigger number, is the mass number, protons plus neutrons added together, and the number on the bottom is the atomic number, just the number of protons, which is also the same as the number of electrons if it's a neutral atom. Finally, on the bottom of this worksheet, the only thing that's different is now we've arranged the columns vertically. So each of these vertical columns is for an element for which you have to provide this information on the left-hand side. If you're confused about how to decide if this element or isotope is stable, read and reread this section right here, which explains how you can calculate the neutron to proton ratio. It's really pretty simple. If you cram too many things into the nucleus of an atom, it can become unstable. But there's a special magic zone where the atoms are stable. And the way that you can calculate that is really simple. Divide the number of neutrons by the number of protons. If your answer lies somewhere between 1 and 1.5, you can write yes, that's a stable atom. But if it's smaller than 1 or greater than 1.5, then no, that's an unstable isotope. And basically it means it's going to start emitting radioactive particles. So if that confuses you, just hold your questions, but I think it's really simpler than you want to make it. Now that's a good stopping point. I'd like you to go get these worksheets, go to work on them. I would say no more than about maybe 15-20 minutes at the most, because the second concept that you need to do is to understand how to calculate average isotopic mass. So if you're substitute, we'll stop this vodcast right now. Let's stop and take about 15 to 20 minutes to work on them. See you in a few. Okay, so I'm back. And now what we're going to do is we're going to take a look at what are different versions of the same element. So the atomic number, as you learned, is the number of protons that are in the nucleus. It's a fingerprint that identifies the element. You change the number of protons, you change the identity of the element. So it will also determine the element's position on the periodic table. Now, all elements of a specific element, all atoms of a specific element have the same number of protons and electrons, but they can have different numbers of neutrons. And we give a special name to these forms of the different elements. They're called isotopes. Now again, let's review. The number of protons plus neutrons is the mass number. So if you had 3 different isotopes, you will have the same atomic numbers, but different mass numbers, because some versions of that element will have additional neutrons. So we've got a picture that's going to come up to you showing how you can calculate something called the atomic mass. It's not the same as the mass number. It's related to the mass number, but it's what we call a weighted average. And a weighted average takes into account that there are varying percentages of the different isotopes out there in nature. Now that's gibberish to you, so hold on to that thought. Dalton was able to assign relative masses to the weights of the atoms. So he used hydrogen as a standard and said that has a mass or atomic mass unit of 1. So since oxygen is 16 times heavier than hydrogen, its atomic mass units are 16. We really use carbon now as a standard of comparison, but the point is, sometimes those masses might be different. Here are 3 isotopes of potassium. What is it that makes them same? The number of protons. The atomic number have to be the same or you can't call it potassium. But what's different are their mass numbers. And notice that we can have one extra neutron or possibly even two extra neutrons. They're not really extra, it's just a different form of the element. So if that's my mass number, and here's my atomic number, simple subtraction can show me that I have 20, 21, and 22 neutrons respectively in each of those isotopes. Now coming up is a slide that will show you that the abundance of these isotopes in nature can vary. Let's say you had a special gun that could go out sniffing out potassium isotopes. Well, 93.25% of the potassium you'd find in nature is that version. But about 6% of the time, you find a potassium atom with extra neutron. And at less than 1% of the time, you can find a rare potassium isotope that has two extra neutrons. So what we're going to do is called a weighted average. The calculations that are coming up on the screen are not going to be very helpful, but essentially it works like this. You will take the percentage of the abundance of each isotope, turn that into a decimal. You will multiply it by each one's specific mass, and then you're going to sum them up. When you sum them up, what you will see is what we see on the periodic table. We don't see over here in the upper right corner a whole number. We see a number with a decimal fraction. And the reason why it's not a whole number like a mass number is because we got it by doing a calculation that I'm going to show you now. So please locate this worksheet. First thing that I would like you to do as you locate this worksheet is circle the fact that it's got to have 4 significant figures in each of these answer boxes. So let's look at our sample problem, let's look at another one, and then you're going to spend some time calculating the average atomic weight or mass of these various elements. It's also called the average isotopic mass. So if you go out in nature and you search for hydrogen, almost all of the hydrogen you find weighs 1.008 atomic mass units. A tiny number weighs twice as much. So what you do is you take the percent and turn it into a decimal by moving the decimal point 2 places to the left. You multiply it by its mass of that isotope. Lather, rinse, and repeat. Do it again. Take 0.02% and go 2 places to the left. 0.0002 times 2.014 equals this number. Now you add them up. And you have this number sitting in your calculator when rounded off is 1.008 atomic mass units. Now that's a lot to digest, so let's look at it one more time. Calculate the average weight of boron if 20% of the boron you find out in nature weighs 10.013 atomic mass units per atom, and the other 80% weighs 11.009. Percents always get turned into decimals by moving 2 places to the left, times it by its mass, leave that number sitting in your calculator. Do it again. 80% is 0.800 times 11.009. Leave that number sitting in your calculator. Now add the two together. In my calculator, I saw the answer 10.8098. Rounded off to 4 sig figs, that's 10.81. Our point would be that whenever you do one of these average isotopic masses, the answer that you get will not be the same atomic mass for any individual isotope, but whichever one you have the most of, like in this case, 91% of neon has this mass, your answer that you're going to get will be closer to the mass of the one that you have more of. So one more time, that's what we call an average isotopic mass. It's a weighted average, not like a simple average. You take into account the percentage abundancy of each of those isotopes in nature. Okay, that's it. Hopefully you'll be expert at this, and I'm going to ask the substitute to shut down the podcast right now and let you guys go back to work.